All right, we're officially started right here. A couple of things I want to mention. I sent a recap from last week. Hopefully everyone can hear me. Last week we talked a little bit about GWR. Today we are going to finish talking about today we're going to finish talking about the extraneous issues that we deal with in geostatistics. We're going to go over the final exam and then we'll be done for 2 weeks. And the final will be in 2 weeks from today, sitting right here. Because today I am going to be on the road to where my wife wants to go for Thanksgiving. So, so we should be set with that. Yesterday we had some defenses. They were really good. And then also tomorrow we are hosting GIS Day. So we've got a GIS Day. I'll kind of show you the flyer here, but these are former students who like literally sat right here and they're going to be talking starting at about 11 o'clock. We're going to have a couple people talk about their experiences at 10:30. I'll do an intro, but Rebecca, Nelson, Roderick, Mike sat in the back right there. He made that poster. Corey made that poster right there. Rebecca used to sit back there. Nelson was always in the back right there because, I used to have like my front desk up there. And then Roderick. But these are all people who work for NCDOT, Department of Environmental Quality, the county, and I forget what the name of the company she works with, but she's starting a brand new she's starting at a brand new position. So these are all students that have like graduated in the last 10 years that are like out doing GIS and stuff. So I want them to come and talk about their experiences. We've got food in 12-1229 right back there. So we got food, come for food, come to talk, come to meet with them. Really good, these two kind of work together over at NCDOT. There's always NCDOT internships. Nelson started with an NCDOT internship and I liked him so much that I just kept him on. And now he's been there, he's there, he's been there for a while. I just like success stories because I think a lot of times I just sound like your parents or my parents and just lecturing, this is what you need to do. And, I think, your colleagues, your future colleagues, the people who are out there doing it, I think are much better examples to tell you some of the technical skills, soft skills, everything else so that you can, be successful in the workforce. Because at the end of the day, the workforce and the job markets, it's pass fail. You either get the job or you don't. People complimenting you on your resume and your interview, that doesn't mean anything if you don't get the job. That's all we want, right? And no one cares about your GPA or the classes you took. You get the job. To me, that's kind of the most important thing out there. How do we get Andy a job? How do we get Philip a job? How do we get Michael or everyone here or the people joining us on, how do we get you a job out there? The 4.0s, they don't mean anything. Maybe it'll help you get the internship to help you get the job, but that's about it. And so these and the ever important soft skills are really important. I was talking to Corey last night and he's just, even the people they're hiring now from when he got hired 6 years ago are, you see, in a kind of different tenor to the type of students entering the workforce. And I really try to encourage people is like, let's do the easy stuff. Like, what's the easy stuff? What's the stuff that doesn't take talent? What are things that you can do at your job that don't take talent?
Dr. Maroney.
Yes.
I had a question for the event on Thursday. Would that be something you recommend us bring our resumes to, or is it kind of like more informal, even when we're talking with them after?
More informal. Yeah, I would.
Okay.
I don't think they would be in a position to give you a job or anything. Most of these people in their 20s, 20s, early 30s. So, but if you want to meet them, like, hey, they'll let you know when the next opening is. And they're probably, I know Corey is on hiring committees for the next GIS tech for the city of Durham. So, go and meet them and say, hey, when's your next tech position opening up? Let me know. And that would be good. So probably not resume, but they aren't that high up in the food chain yet. So But that's really good thinking. I didn't think of that. But I think
Okay, thank you.
thanks. This is going to be a little bit more informal where we're going to just not sit, but I'm going to ask them questions. I always have like not funny, but stories about each of them. And then we'll ask about what do you do every day? What software do you use? Because, Corey does something called Arcade, which is a programming language that's kind of like Python for online. Daniel's really good at JavaScript. Why do you use JavaScript?
Well, so what we're gonna do is for stuff like code, for example, like
Package management, and also isn't JavaScript used for like web pages?
yeah.
Yeah, so used for web pages as opposed to Python, which isn't going to integrate as well. To me, Python's the scripting language for our GIS software. And so we talked a little bit about that model development. Mike, he does lots of stuff. He's really good at ArcGIS Online. He did some neat redlining projects. He was like my go-to for everything. Roderick worked in utilities. Nelson worked in DOT. And Rebecca is probably one of the best cartographers I've seen. The maps that she's made are really, really good. And so if I think of it before I get onto campus tomorrow, I'll kind of bring up some of the stuff that they've done as part of my class. I'm sure a lot of the things are much better than, much better these days. So I encourage that. But like I was saying, and even with Corey speaking to him, like do the easy stuff, like everything that you can do. Show up on time, when we go to conferences, dress nice, all those other things, I kind of joke with some of our faculty members when I deal with students who are like, this person's a jerk, that person, it takes no effort to be like nice. You know what I mean? It takes no effort to be, nice. I'm still not going to let you turn it in late, but I'm not going to, you know what I mean? I'm not going to let you turn in your paper, December 11th, but, you can be nice about it. If you turn it in, an hour late, that's fine. I'll take off some points. I'm not giving you a zero. Thank you. I'm not giving you a zero, but it takes no effort to do some of those things. And I think a lot of times, especially when you're working in a group environment, I think a lot of times people have kind of fallen off that. And people, I mean, like people I work with, and it's hard. And you can do so without compromising your ideals, because I got deadlines and all those other things. I've been dealing with tons and tons of deadlines. I'm sending stuff out, and so I do unfortunately have some of these hard deadlines from time to time. So I encourage everyone to just go. I posted a link to attend online, but to me, looking someone face to face, I think is really, and making eye contact with them is important. I sat on a meeting today at 1:00 and I got 3 screens going on and another video, TV screen. And I'm just waiting for my name to be called so I could just say something, to pretend I know what I'm talking about. Really, you know what I mean? Especially when you got these online, oh, I'm sorry, Andy, you were at the meeting today. So, forget I said that. Okay. No, but I did have other things, I got some other things. I'm answering emails and all these other things as they come in. And so, you really can't dedicate your full attention to those. And we kind of know the era that we're in. Couple other things about announcements, because I know people they're here to look at the exam. So we got GIS Day recap. I'll talk a little bit about this here. I'm going to do a couple little demo stuff tomorrow. Always check out like the GIS Jobs Clearinghouse. Here's one in Sweden for US residents. So I thought, not Sweden, Norway. But Norway, that looks pretty neat. Capital Park Planning Commission, postdoctoral fellow in economic geology. That's pretty neat there. But these are some of the jobs out there. Also USA jobs. This is really good. These are just a little bit more difficult to get just because they are. Department of Homeland Security, paying, $28 an hour, about $56,000 a year. But you can see some of these jobs out there, really good opportunities here. So apply for these. Let us know if you got any questions about cover letters. If you see my email signature And has anyone ever seen my, my cover letters? Okay, good. So if you've ever seen, stuff, but if you've ever seen my email signatures, I have my texty thing doesn't work here. Okay. I'm gonna get a little call here. Come on. You guys have to do this too or no? Thank you. Okay. But for this one here, we've got sample job employment letter. This is for Corey, one of the people coming tomorrow, and we wrote a cover letter for him so he could get the job at Durham. So this is, December, he graduated about 6 years ago. This was the cover letter that he submitted. Um, Obviously, the cover letter wasn't in red, but what do you think these red words are here? These are taken straight from the job description. Why would I pull stuff straight from the job description? Because they're using keyword matching for a lot of these. And so what's keyword matching mean?
Keywords from the job description.
Look for the keywords from the job description in your cover letter. And so you can see exactly, we made sure we did QA, QC, internship, parcel data, GPS, all these other things, even though we didn't do too much GPS collection, especially before field mapping was offered. But he took the entry training course on GPS collection because we didn't do it in class. So he just went through, took the 1 hour GPS collection course. Okay, GPS data, geospatial databases. And so you can see everything that we have. Some of the things that speak to your soft skills right here. Quantitative statistical analysis, that's basically this class. So we're going to do an overview of some of the go-to tools that I talk about. Foster communication, perform QA, QC. What does that mean? What's that? Make sure the data isn't screwed up. Now, how do you do that? Sometimes you look at it by hand. That's what students do, you know what I mean? That's what I used to do back in the day. Hey, let's make sure these firing ranges are match up to range 1, range 2, range 3. Let's make sure the speed limits aren't negative numbers or really big numbers. So when I go type in my driving directions, it doesn't give me wacky times. That's what QA QC is. Now, also performing GIS troubleshooting, technical assistance, fostering communication, which is always important because to me, basically, if you don't market your GIS skills, then you really don't have GIS skills. Like I hate to say that, and you can be a tech and you can make good money sitting in an office, but to move up, you've got to have the technical experience and you got to let people know how well you do stuff because I'm not going to let people know how well you are. I'm going to let people know how well I am. You know what I mean? So the marketing of yourself is really important. Now, me being the professor, I'm gonna, someone called me up, I'll tell them how great you are and all the things that you're good at. But when you get out in the workforce, you're gonna be the only one advocating for you because everyone else is gonna be advocating for each other. My wife works in a union shop and she works, really hard to kind of stand out. And there's people who kind of do the same thing and we do the same thing here. But this was a job letter. One of the other things as part of this job letter was he had a supplemental question. So he had to go and answer certain questions on the application. So he had a cover letter and then they said, what GIS software are you using? What's the difference between data precision and data accuracy? We hear those in class, right? We kind of interchange those, but they're really a little bit different. In this class, we haven't talked too much about those. But so he was asked to answer a few kind of technical questions. And so if we think of it tomorrow, this is the supplemental answer sheet that he wrote, as well as the sample cover letter that he wrote to help get him the job down at Durham, Durham City Works, which he's got 6 years later. He's been there for 6 years. And he just came to us from community college and created some maps on ulcerative colitis and has gone on and done some great things. And those are the maps he created when we were looking at death threats and things like that. And he got an internship up at Woods Hole, which is NOAA, National Oceanographic and Atmospheric Administration. So he did some really good work up there, working with paper maps. You know, it sounded tedious and boring, but yeah, it was tedious and boring, but you can put on your resume, I worked at Woods. Okay, anything else before I stop sounding like my parents here? So, all right, so, and I'll kind of go back to the go-to tools at the end, but what we were talking about last week were kind of circumventing issues about quadrant size, study areas, things like that. The next thing we're going to mention, because all my papers have something called the discussion. These are all the things that I could have done differently that would have yielded different results. And those are some of the things when Philip and I are meeting, and Will and I are meeting before class to talk about, well, what are all the different ways to measure proximity? Because we made this, or he made this blanket statement to look at the relationship between income and socioeconomics and proximity to emergency shelter locations. And this word proximity means a lot of different things. You know, we're looking at drive time between what? Between centroids. We did population weighted centroids. We also did point polygon. We ran some spatial joins. How many of them are within each? And so we're looking at all the different ways that we can express proximity, availability, accessibility, all these variations of that. The other metric that we have is MOP, modifiable area unit problem. So the actual size and shapes of enumeration units, or sometimes we use the word aggregation units, might change the results of our analysis. I thought this was a really neat picture here where that we have these points here. If we group them into our nice little quadrants here versus these units versus this unit, you can see how our units change. Now, we love quadrants because of they're nice, equally spaced. We don't have to calculate density or anything like that. But in reality, we work with units that look like this, not necessarily this, but look like this when we look at counties and block groups and census tracts and all these odd units right here. So sometimes we do run into issues like this. So this aggregation, other issues with MOP, modifiable area unit problem, is that I work with quadrants versus zip codes, and then we can start to look at relationships between these, and you can see these relationships between our quadrants and our zip codes are very, very different when we run just two-dimensional, we run regression or correlation against these here. So I think these are really neat. A couple of my early papers, you'll see something specifically said to MOP when I said, hey, I ran these at the block group level, but when I ran these at the tract level, I had the same general results. Because you might want to get an answer like this, and then when you run it with, hey, let me do this, I don't get what I like. Let me run it with the different units, and I get a nice, a nice relationship right there. Hey, I'm going to go with the zip codes as opposed to the quadrants because I get the results that I want. And so you can see, and this is taken from the book, but we want to ensure consistency with varying reliabilities across enumeration units, aggregation units. Oh, this is taken from my paper. And I was like, this looks pretty good. I wrote this. Okay, but you can see that we ran these at various levels for tracks, and we saw that there was consistency when we agglomerated these data at tracks as opposed to block groups, because I'm sure at some point in time in a review, someone asked about that, and so we addressed that. With any of my papers, feel free to cut and paste and then paraphrase, because if you cut and paste it, someone's going to find out when they run it or whatever here, but also use it as a source. So a lot of times, and I was working with a master's student yesterday, we had a couple of really good master's defenses, And they're like, I'm having trouble writing a lit review. And I was like, no, you're not. I already wrote the lit review for you in this paper on food deserts in North Carolina. So just go and paraphrase what I did, use the same sources, and maybe find an extra one on your own in the last couple of years since I wrote the paper. And you don't have to write a lit review. I wrote it for you. And so kind of think smarter instead of, or work smarter instead of harder. Don't write a brand new lit review. So like you do with the car collisions. Someone's probably already done this for different states or at the national scale or whatever. Maybe no one's done it for North Carolina. This is where Cameron Schuler can come in and add his own work here. But for the lit review, you're going to do, so-and-so did it at the national level. So-and-so did this in New York. So-and-so did this in Southeast North Carolina. This is just at the state scale. And so not feel free, but take advantage of all the other research that they've done, because guess what? You're going to be doing that research too. You're going to be adding the new paper that was done in 2024 on, deer vehicle collisions in North Carolina or whatever. So we've got these study areas. So we have our quadrants right here for this 3 study area versus what are we looking at here? These are going to be census block groups versus census bigger quadrants versus, I don't even know what census tracts right here. So you can see this modifiable area unit problem. We've got zip codes, census tracts, and the relationship between these. So when I run things like spatial mean, spatial median, these standard deviation ellipses, you can see if I'm grouping them at different scales, just at the centroid level, you can see how the size, shape, direction, and complexion of these are going to change, which I think it's really interesting, to be honest with you. Another thing, and we just got done with this election thing, is that sample sizes that we use. I've got some map stuff here, but we got sampling error. We hear about this sampling error, and we hear for a couple of elections in the recent past how one side was going to win, and magically the other side won. And how? Because everyone told me what was going to happen. So we have this margin error right here. Now, when we talk about this margin of error right here, this N stands for sample size. These are probabilities, 1 minus, this is the expected probability, 1 minus t hat. But our margin of error is going to be dependent upon our sample size and our representative size here. And so we can start to throw in plus or minus. So this margin of error for 10,000 samples is, or 10,000 samples plus or minus 1.3%. So when you start to see these things on elections, and especially in the census data, you go to the census data, it's going to say, give me the median household income for every county in North Carolina. That margin of error is going to be a lot less because we have a higher sample size than at the tract level, and then at the block group level, and then we collect these data at the block level. And it'll say margin of error, $20,000. So if the median household income in a city is 80,000, or typically a block group or a tract, 80,000, it could be 60, it could be 100. It's a really high margin of error. So if you're working with some of these kind of low sample size block groups, we run into this with block groups with some of the really obscure data, like number of Danish people who live in a block group. It could be, it's like 6, but it could be -4 up to 16. When we have those really odd margins of error. For things like income, population, race, and age, they're really pretty tight. But we look at access to transportation, and we bring into something called imputation. So we run into these issues here. So if you have like sample size of 10, we're like just using the math, it's like plus or minus 44%. Why even sample something with 10? Like, seriously, why? Start to get to 100, sure, 1,000 here. And so when you start to download some of these data from the Living Atlas, they might not come with these margins of error, but know that they exist. Another thing that we have is small number problem. This was taken from the North Carolina Department for Health Statistics, and we looked at the infant mortality mortality rates for various counties. And you can see some things here. We've got some really kind of, I don't want to say wacky values right here, but we can see PCR, but for Alamance County, the total infant death rates, which are infant mortality rates, deaths of kids under the age of 1. But you can see some of these here where they're really high or really, really low, or they might not, they put a little star right there where in small districts, the incident rate of 5% might be derived from 3 cases of disease among a population of 60. So they're really good about explaining some of these things right here, where that, look at, we're in Bertie County, we have non-Hispanic African-American rate here. We're in Bladen County, non-Hispanic American. Look at the American Indian rates in Bertie County and Bladen County right here. Why is it so high? Because it only had 1. Are there a high amount of American Indians in Bladen County? Probably not. And so we're looking at a really, this number is really going to shoot these numbers up high, where I look at Anson County, non-Hispanic, other deaths, so like Alaska Native, Hawaiian Pacific, or whatever here. And so I think it's really interesting when we see these values here that are really high. I don't want to map the non-Hispanic other rates because I've got values of 3, 4, 0, 0, 2, 0, 0. Useless. And how do we circumvent that? We can take these over periods of years, or we can just include these as part of our other calculations here. But even here, we got 14, 1, 1, 4, 1, 2, 8, 4, 3 for total infant deaths over a period of a year. So we've got some really kind of wonky values right there. And so we run into some of these issues a lot here. We have Cleveland County, and I kind of showed some of these other counties like Gates County. Gates County, I think this is African American. This is Western North Carolina. It's not a high African American population to begin with. So when you have 1 death, it's going to shoot it up extremely high. And so we can look for these different age and race and ethnicity cohorts across these. Another issue that we have with the small number problem, and I showed this before, where that New Jersey is divided into sub-county units called townships, towns, boroughs. And you can see the proliferation of deer. In this case, these are black bear sightings from 1995 to 2009. So these lighter areas show where they are across all of the state, where that only in 1995 they were concentrated in this darker area here. But you notice here, there's not one here, there's not one here, but they're all around there. Why are they all around here except for this little dot right there? So what's so special about it? And this is actually where Dr. McGinn is from. He's from like right over here. But we've got these kind of little areas here because these are so small. So what are the chances of a bear wandering through this as opposed to this big area here? Really, really small. Now, how do we circumvent that? We just create our nice little pretty little quadrants, right? Create a nice quadrant so they're all the same size. So we didn't have to deal with things like this. But at the state level, the New Jersey Department of Fish and Wildlife, they capture data at this scale. They don't know what a quadrant is. I'm sure they know what a quadrant is, but they don't. They capture it at this scale here. The other thing is residual mapping. What's the residual? Leftover, literally leftover. Like when you create a model of y equals mx plus b or some of these more complex multi models, you're going to throw them basically into a big equation. So you can use multiple independent variables to predict a dependent variable, COVID rates, by mail voting rates, or whatever we looked at, height and weight. And we're going to look at height and weight as part of the exam. Maybe you'll download the Excel spreadsheet and open it up and have it right for the exam. But these residuals are basically what the difference between the predicted and the actual are. And so in theory, when we map these residuals, they should be evenly distributed about your zero line here. In theory, above your positive z-scores, your negative z-scores, if we were to standardize these. Now, yesterday, someone did something really neat with z-scores. And today, Michael and Andy, you came to the talk yesterday. One of the students, what he did was he went and used a survey from our field mapping class created a little survey, and he went and collected all the information for the price of gallon of milk, pound of bananas, 16 ounces of steak, mac and cheese, loaf of bread. And he went and collected these over every 2 weeks for a period of a year, and basically mapped these. But you can't really compare price per gallon, loaf per bread, and he did it on a store-by-store basis, which I thought was really, really neat. So which stores were the best? Walmart was actually the best. And then you had like Sprouts and Fresh Market, which were the worst. And then you kind of had Dollar General somewhere in the middle, because we all love Dollar General, but when it came to like bananas and milk and eggs, it was somewhere in the middle. But even then with their eggs, eggs got too expensive. They just didn't sell eggs, which I think is kind of smart or interesting or whatever. And so, but he said, hey, I want to compare the stores, like, hey, which store has the best? Because you can't add them all up, right? You can't add up, 253 plus 3, because they're different units. Imagine adding up 2x plus 3y. What's 2x plus 3y equal to? 2x plus 3y. You can't do anything with it. It's not 5xy, not any of those. It's just 2x plus 3y. And so he wanted to keep those units. So he created z-scores for all these. Because what are the units for a z-score? There are no units. Excellent. And so he went and added up the z-scores. So, hey, this store had the lowest z-score, because when we averaged up all the banana prices, this was below the mean, this much below the mean, versus the loaf of bread, versus the pound, versus the pound of ground meat or whatever. We were looking specifically at in a 8-ounce jar of peanut butter. And we were looking at about 8 or 10 of them. And you mapped the volatility. It was really neat, because 90% of it was actually getting the data. We're going to talk about some of the go-to tools in a little bit, and then we'll start talking about the exam. People are perking up when I use the word exam here. Okay, so we got that residual mapping. Other things that we just run into, we got some big fancy words here. One's called multicollinearity, where that, in theory, independent variables do not be correlated when running regression. Meaning, hey, I want to look at the relationship between COVID rates, and my independent variable is going to be white versus minority. There's a direct inverse relationship between white and minority. So essentially, when you do this, what are they going to do? Cancel each other out. That's all they're going to do, is cancel each other out. And so what are some things you can do? Keep the variable, eliminate them, or there's something, we don't have it in ArcGIS Pro, but SPSS has something called stepwise regression, which will go and kick stuff out. You heard of that before? Stepwise. And so when we look at something like white versus percent minority, you can see the direct inverse relationship where that, all right, this one is 84% white. Basically, minority is just non-white, so obviously this is going to be 16% minority. And so you can see the relationship between these. So if you were to map these as independent variables, they're essentially canceling each other out. Another thing that we have here is called heteroscedasticity. So that's the variability. Now, what's this word variability or dispersion? I use this term z-score. What does variability mean? It varies from what? The mean. The mean. In this case, this is going to vary from the line to best fit, that y equals mx plus b here. But we have something here called heteroscedasticity. Basically, that means as the independent variable increases, there's more variability in the y. Okay, so your r squared is going to increase as we go further and further to the right, or we increase here. That's just an example here. The last thing that I love talking about are the idea of neighborhoods. How do we convince around? Just like with Philip, we said, proximity. What does proximity mean? We ran a cluster analysis, because I'm going to kind of start talking about my go-to tools that I talked about in this class right here. And there's lots of other go-to tools out there. There's, you're just getting a little sample of Maloney's go-to tools that you'll see in my papers. But the conceptualization of neighborhoods, because we have a lot of different neighborhoods. And how do we conceptualize distance? The idea of distance. We have Euclidean distance, we have mapped, we have something called Manhattan distance where we travel at right angles, and then we have drive time, which is most practical. Now, Euclidean distance will be practical for some things. When I hop in a car and drive, but when we're looking at like dispersion of, gas or whatever, it doesn't travel along roads, it just travels in the air. We have adjacency or neighborhoods. And so for this hexagon A or polygon A, what are its neighbors? What are its neighbors? What does IDW tell you a neighbor of A is? Well, IDW means, all right, these neighbors have more of an impact than these neighbors here. But we can define what it is. We can say inverse distance weight. We can set a boundary, or we can just say anything that touches it is a neighbor. Now that becomes problematic, especially in North Carolina. When we go out to eastern North Carolina, and not much touches anything, or you have these really odd shapes. Or we have interaction. That's kind of the IDW, where that if we move further away from something, it's going to have less of an impact, that weighted average that we have. I've done some good work with this here, so you might see a couple of formulas here, but distance, the magnitude of spatial separation, it could be Euclidean. Adjacency, what's the word adjacent mean? Next to, okay? And in a file geodatabase model where we have topology, this is a new word that I'm throwing out here. What's the word topology mean? Like that? The arrangement of elements. What's topography then? Elevation. Now, let me see. Oh, real quick. That letter that I had from Corey here. Let me make sure, because there was one of them. Okay, this wasn't one of them. Okay. Okay, this one asks about accuracy and precision and a problem that you ran into. But we had another letter with a student that said, explain the difference between topology and topography. One of those letters where they said, hey, you got to start speaking to your skills. Corey, he had a letter where it said, explain the difference between accuracy and precision. See, and who knows that? Okay, maybe we'll go back to that. Okay, we have adjacency and neighborhood, and then we have interaction, the strength of the relationship. And that's just exemplification of Tobler's first law of geography. Because distance is not simple here. We can use my distance formula up at the top there, but it's not going to be practical for everything. More particularly, we use spherical distance here. But when we use state plane projection, we're basically flattening it, sticking a 0, point down in Alabama somewhere, and we're calculating distance here. Other things we have, distance through networks, time, or friction. What does this word friction mean? Rub in here, but what would be examples of friction that you work with? Friction along a network. What's a network? Set of lines, right? A line network. Like sewers. In sewers, what would be friction? Width of a pipe. You got these really small pipes, not as much can go through it at the same time. Speed limits are a type of friction, or stoplights are a type of friction that we can look at. And to me, it's really tricky or interesting how we express those, because we look at those through attributes. Because to me, I think of friction like this. I'm driving from here, I'm driving from there. It gives me all the different directions or ways that I can go, and I care about one of these. Other thing, what is a neighbor? Well, like Philip alluded to, we have borders, and then we have corners and borders. So we have a little corner. Now this is a neighbor versus this is a neighbor. Where that, hey, I just want to look at the nearest 12. The nearest 12 are going to be my neighbor. A certain distance is going to be my neighbor. Or as I just keep moving further and further away, you're less and less of my neighbor. Okay, you have less and less of an impact or weight on me. And then we have these neat things like hexagons. In the field of geography, like hexagons are really like special units as opposed to squares, because everything within this hexagon is closest to the center point compared to other things. So it's like the perfect decent polygon, perfect surface area if we were looking at like a lattice, or like fishnet. It's kind of the perfect fishnet, the better fishnet than this one here, But you can go down some rabbit holes with these because in reality, what do we care about? The world isn't this. Maybe the world is probably closer to this. This is the world, like this is a neighbor right here, And so we got 4 neighbors right here. So when we look at Maine right here and we look at neighbors, it's got 1 neighbor. And so what is your relationship between you, the mean, and your neighbor? You're only working with 1 neighbor, like you're either in a hotspot or you're not in a hotspot or whatever. We have second order calculations right here. So these are second order with your hexagon, with your queen. And then other things that we've talked about with some students, contiguity edges, inverse distance. These are all the different conceptualizations of neighborhoods that we can work with. Inverse distance squared, fixed distance band, zone of indifference, K nearest featured. I'm not a big K function person. Contiguity edges only, contiguity edges corner, and then we get spatial weights from a file, which I've never done in my life. And so I don't, you can create those or do whatever you want with those. And so when we go to our conceptualization of spatial neighborhoods, so this is a project that a student did where we were looking at hot spots and cold spots of crime. This is using one neighborhood, fixed distance span. This is using another neighborhood, contiguity edges no only. Same exact data. One set of hot spots and cold spots using one conceptualization of neighbor or distance or neighborhood or whatever we want to call it. Here's another. Which one's right? I don't know either. You know what I mean? So you can still tell your story using the same exact data. And so we'll talk about some of these go-to tools in a little bit. So we'll talk about some of these here. Spatial interaction models. I'm almost done with these here, but we have something called the gravity model. I like these. We had a student who did this a long time ago because all this is, as you move further and further away from something, the attraction is going to be less, but it's also going to be impacted by weights. 2 things that have higher weights or higher masses are going to be more attracted to each other than things that have lower masses. That's why everything goes around the sun, right? Because it's got the highest mass. And so when we look at the spatial interaction model, we can look at the relationship between 2 things. Because a lot of times, where do they put hotels and hospitals and all those other things? They put them in low population areas. Oh, why not? Because there's no one there. So you're going to have to travel to get them there. And so that distance is the denominator. So that kind of serves as friction or deterrent or whatever. We want things as big and as close to each other so that basically our interaction is extremely high. So we had a student about 7, 8, 9 years ago do some really neat work with this, with these spatial interaction models. I've kind of fallen off a bit on these because you kind of start to look at, where are we going to start to put things so that people are going to be attracted to it? Has anyone heard the what's the store? McKay's? It used to be in Greensboro called Edward McKay's. Yeah, but they moved it all the way out to Mebane. And I'm sure someone did some, I'm sure it was due with zoning or whatever, but I live in Greensboro. It's too far away for me to go there. But someone did some work like, hey, we put it in Mebane. We might get some Greensboro people. We might also get some Durham people where you run these spatial interaction models and say, hey, what's the zone of interaction between these, which I think is interesting. Now, I drive by it to work, so if I really wanted to, I could just stop by and do it instead of it being 10 minutes down the road where I used to live. So we can look at the amount of interaction between Shanghai and Wuhan and these other cities right here, which I think is kind of interesting, really interesting. And there's some definite business applications here because when we look at these spatial interaction model, it kind of represents Newtonian physics, where we have sizes, masses, as a function of, R squared, but it could just be anything, any type of distance, which is gonna serve as the deterrent or the friction or the separator between two things here, so that most of the people in Greensboro, like, I'm not gonna go, it's too far away. What's far enough away? What is far enough? Are you gonna drive 20 minutes? You have 30 minutes? To me, my grandmother, anything more than 20, my grandmother lived in Rhode Island. So, like anything in Rhode Island, like if it was more than 20 miles away, it would be, it's too far away. Like 10 minutes, my grandma she wasn't driving. Like she, drove an hour and she had to brag about it. But she never even drove to my parents' house and it was like 4 hours. Like 4 hours, I could do that. I do that when do that in my sleep. We had to fly her. It took long to fly the lady down here. So, but all kidding aside, your spatial interaction, what's the distance that you're gonna be willing to? It's gonna be different from Cameron versus Andy versus everyone else here that you're willing to travel to go to something. I don't mind. Some things I don't necessarily mind. This is some prior work that the student did where we're looking at the attractiveness, the force between a census block group and farmers market is a function of push factors and pull factors in inverse proportion. We talk about, especially in Dr. McGinn's classes, world regional and world regional and intro to geography, what are factors that make you want to leave somewhere? I left up north. What do you think the big factor was me wanting to leave?
It was cold.
Cold and what else?
Study.
Money, yeah, exactly. Cold and money. I can afford a nice house, a rental house down here, all that other good stuff where I couldn't up there. And then also weather, and then what do people like up there? Oh, they like the schools. So okay, it's kind of I guess the schools are good enough here or whatever. So you kind of make those concessions or whatever. So we looked at push factors and pull factors. So some of the attractions were population, spending on fruits and vegetables. So you want to put farmers markets in areas where people spend more on fruits and vegetables. And then the farmers market, what are attributes that are going to make a farmers market attractive? Variety of offerings, availability. And so how often is it open? So we created a number of different attributes for both the census block groups to basically model how attractive or where we should put them, and then the farmers markets as destinations to make them how attractive. And these are just multiplicative relationships since we didn't have any zero values there. And so we looked at the kind of population by block group, the spending on fruits and vegetables, and we kind of, in theory, we multiplied them all together, but in theory, we should have probably just added up created Z-scores for all of these, added them all up, and the one with the highest Z-score was the place like, hey, we should stick something there, because eventually what we did was we did that, and we did something like this where we said, hey, this is where these are kind of drive sheds, these service areas for the various farmers markets around. And some of these like real small ones right here, we didn't even include because they were like specialized strawberry farms that were open on the weekends, so you and your kids could go pick strawberries, which, but not the permanent farmers markets. Last couple things I'll mention: causation versus significance. This isn't a causation class. This is a where class, and so anything about what causes by mail voting, opinions, COVID. We go to biology, sociology, we go to someone else besides here. So we sit here in the where business because a lot of times now some of these are going to be somewhat intuitive. So when we look at the by mail voting rates, they're going to be impacted by population density and race a little bit and access to transportation. Some of these are self-explanatory, but like race, like I don't know why, that's just what my little model told me. So I might need to go and might need to go and survey 1,000 people, minority people who weren't able or didn't mail in their ballot, and why. So I can look at some of these relationships there. So we can look at less access to vehicles has correlation, but we don't want to imply that causation it just significantly explains the relationship. Because a lot of times we see things like drownings during high times of popsicle consumption, drownings are also high. Well, do drownings cause them? No, of course not. They just happen to occur at the same time when it's nice out. And we see a lot of these things here. It was for years like smoking. Like how smoking was just like so like normalized. My wife was talking about in like the 70s and 80s, like everyone's just sitting around like in the house smoking a cigarette. Like I can't even stand cigarette smoke or any smoke. I'm like, get out, stay away, They just sit around and smoke because they still didn't realize like, hey, these people who are dying of lung cancer, like 99 out of the 100 people were smokers. And the one person was just unfortunately genetically, inclined for, lung cancer without even having smoked. So these longitudinal studies took place over a period of years. And to me, these things are still happening now because I got kids like your age who vape. Like it's no big deal. It's not as bad as smoking. What do you think I say? It's probably worse, but there's not enough study to figure out, hey, in 15 years, these kids who are dying of asthma, or not kids, but people in their 40s, like dying of asthma, what's common about all of them? He probably vaped. So whenever I see it in the car, I just like throw it out the window and they're like, where'd my vape go? And I'm like, oh, I guess you got to go spend another $50 or however. I don't know how much they cost. I don't even know how much a vape costs. I'm looking to see who knows how much a vape costs. No, just kidding. But they're like, there's no evidence out there that it hurts people. Well, it hasn't been long enough of a study to say there's evidence. Some other things here. Other things we've got I want to mention is ecological fallacy. So relationships observed for groups can't be passed on to individuals. So we're inferring from aggregated data, and especially this was taken from my voting pattern data at the zip code level. So like we're between a few thousand, 15,000 people live in a zip code. Like I can't pass the general patterns here. So from all these people onto you. So your friend who's a Democrat in a metropolitan area is more likely to have COVID than someone who is not a Democrat. I can't say that. I can just say, hey, when I look at Democrats in metropolitan areas, they have much higher COVID rates than non-Democrats in metropolitan areas. That's all I can say. Okay, that's all I can say here. Okay, because these data are aggregated at various number of different scales. We're looking at 48, 136, 60, 80, 61 different zip codes here. The other one I love talking about is exception fallacy, because a lot of times when people say, you make a fact and so someone says to you, I know someone who, what are they basically doing? They're supporting your fact. When I say, hey, kids who are, start drinking at an earlier age have higher rates of this, and this. And my wife says, well, I know someone who, what are they saying? Well, yeah, you're right, but I still know someone who, do this, that, and the other thing that have ended up fine. And they kind of ignore everyone else that are obvious, the obvious cases here. And so things like reaching the conclusion based on exceptional cases. So we can look at these are data here. And to me, at the end of the day, data don't lie. We'll talk in a second about how we can express these different data here, but the data don't lie. The data don't lie. Data is plural here I'm using in this case. And so you can look at the average, median, usual earnings for doctoral degrees, professional degrees, master's, bachelor's, or whatever. And so a lot of times people say, well, you don't need a college degree. Do you need one? Yes, no, and these are arguments that we get into. But, so we look at, high school diploma, 853 versus bachelor's degree. And we know lots of people who are less than high school diploma who made this, right? We do. But on general most of the people who don't have a high school diploma make what? That. Okay, that. All right. But we all know, we all kind of gravitate to the exceptional cases. And, I run into these arguments all the time with, family and kids and whatever, and I know someone who they live in Florida and they do this and do that and all these kind of, they retired early and all these great things, but, there's a lot of them and a lot less cases of, a lot more cases of the other folks that we seem to, ignore. And I call this the exception fallacy, because I think a lot of times, called the exception fallacy. So whenever someone says to you, I know someone who, you're going to say, stop using the exception fallacy. You're proving my point as we speak. Okay, so do we want to take a quick break or do we want to go to the exam and get done? Okay, exam and get done. Okay, good. All right, that's what I thought here. All right, so we're going to talk about the exam. I'm going to show you a couple things here and we should be set. So we got the announcements in 2 weeks from today, and I'll post the announcement tomorrow about the what we got going on, because we're not going to be here next week. And so under modules, I've got week 13, which is kind of we're on here. I've got a couple, this is the final exam. I'm going to open up the final. It's not going to be the same exact exam, but I've got a quadrant analysis example sitting right here. So I got a quadrant analysis example sitting right here that you can open up. Does this ring a bell? Hope so. Everyone's been, yeah, it's been a few weeks, but yeah. Remember, we're making that nice, pretty little graph right there with the observed, the expected. I got some expected proportion I've got a fell in here. And so, maybe if I were you, I'd open this thing up and kind of follow along a little bit. And so this is going to be for a few questions. And then I also have a height versus weight. So you have people's height versus weight. We can create just a nice little scatter plot right there, a line of best fit to predict those. And so these are a couple of Excel spreadsheets that I have right here. And so I'm going to open up the exam right here. So this is the exam. You don't have access to it because I made it that way. And so this is the exam, because at the end of the day, when we look at this here, and I'll talk about a couple things before I go through it here, is that, we talk about our go-to tools. And when you write papers, people don't want, what do people really want to look at in your paper? They want to look at pretty stuff, maps, the intro, the conclusion. If they're really interested in the methods, maybe a nice little flow chart diagram, but me, I don't want to read everything unless I'm really, really, really interested or someone's kind of paying me to review it. And so these go-to tools that we talked about in this class are things like descriptive statistics, mean, median, mode, okay? Descriptive statistics. So if you have median household income, COVID rates, all these other things, very first thing you should put, hey, for all 763 zip codes, this is my average, COVID rate. This is the high. This is the low. And so when we look at dispersion, we've got high. We've got low. We've got standard deviation. These are just some really simple things to describe the data set. Now, how can I express dispersion graphically? What can I express it graphically? Dispersion. How the data look. Express those graphically. Little graph. What's that thing called? It's not scatter, but you're on the right track there. That would be something slightly different. Histogram. We're back in first week here. So we got this thing, this histogram. Just to look at how the data look before we even start talking about things. This is how the data looks. Now we got descriptive. Now we have spatial mean, spatial median. We're talking about spatial data here. Now my go-to tool for what? Clusters. Okay. Hot spots, cold spots. Okay. I love those hot spots, cold spots. Now, can you just magically click a button and say, I want to make a hot spot, cold spot of population? No, because is population going to be normally distributed? What type of data out there are going to be normally distributed or at least normalized? Give me an example of some normalized data. What did you say? Rates, exactly, rates. Crime rates. Now, even these days, death rates, are death rates normalized? They kind of are, but you got to go through and age grade those. But crime rates, median age, median household incomes. I love this normal distribution, because that's what data typically looks at. We're in an NFL season and we don't have a lot of teams with 0 or 1 wins. I don't even think there's any teams with 2 wins. We only have like one team with 10 wins. Most of them are somewhere in the middle right there. And so we want to create these with rates. So these data just don't automatically and magically curate themselves. You need to curate. You're the one who curates the data so that when we show up tomorrow, you show up in a conference, we're looking at rates because someone's going to say, hey, you don't have rates there. And I didn't even put that in the discussion because I think we should be past that point. So we got these clusters here. Another thing that I love are p-tests. Why? Because I can extract these right out of my clusters. Hey, all the hotspots. What's the median household income in the hotspot? What's the median household income in the cold spot? Really easy. This is a combination of an aspatial and bispatial because these clusters, these hotspots and cold spots, are truly spatial in nature. Why? Because I spent the last 20 minutes talking about neighbors. What's the definition of a neighbor? Someone that's near you. Near is a distance approximation, whether it's, inverse distance wave, zones of difference, borders, or whatever we're looking at here. So I'm just talking about some of my go-to tools. Another of my go-to tools here is I like my little quadrant analysis. And why quadrant analysis? I like the multi-step process and the tightly coupling of applications where, hey, I'm going to bring this from ArcGIS Pro, I'm going to make a little fishnet, and then I'm going to put this thing into Excel, make pretty little graphs, and then do some math stuff with existing Excel coordinates, Excel calculations that already knows what a Poisson distribution is. I think it's kind of neat when you start typing P-O, and it knows what it is. So this is stuff that I'm making up. But a Poisson distribution is just a normal distribution curve. That's what it is. If you notice in title, it's the end of a normal distribution curve where we're doing this for count data as opposed to basically other data, what we call Gaussian data. I think I've used that term before, but Gaussian data could be, has very high granularity. It goes to like decimal points and all that other stuff where that count, you can't have a count of 1.3. It's 0, 1, 2, 3, 6. Number of, so that Poisson's just a little bit different than that normal distribution there. So we have these tools here. I like my t-tests, I like my ANOVAs, but these are what we got to go to prove. And I talked a little bit about my Jacquard index. And right now I'm kind of thinking of ways so that I convert these indices, which are just numbers from 0 to 100, converting these to p-values based on sample sizes. And I think there's really big gaps in my thought, but I don't know, maybe someone will give me money to do that in the next round of grants. So who knows? Right, so we've got these kind of go-to tools. So these are mine. There's lots of others out there. These are just kind of, we got before and after and all these other things, different variations of your t-tests and your ANOVAs. We also saw some of the other types of clustering that we can do because I focus on hotspots and cold spots, but you can cluster in n-dimensional independent space, basically. Hey, I want clusters create clusters based on median household income and travel time and all these other things, in order to create these using fundamentals of AI ML. So we just kind of group them, not two-dimensional space, but 3 and 4 and 5, and then we just use Euclidean distance calculations to figure out this group versus this group versus this group versus this group, where they are along the X, Y, Z, A1, A1, A2, A3, A4 planes and axes. So these are kind of my go-to tools that we're looking at here. So we're gonna look at the exam and then we'll kind of be done for the day. Any questions for me before I talk about the exam? All set? Okay, I'll be done in about half hour or so. But this is what the exam looks like. It runs the same as before. So you can see the points. It'll be running time. Those of you who take the class face to face, I'll give you a password and you just take it wherever you are. It's open note, open book, open anything except for open person. I get a little sketchy, I get a little kind of weird about things with academic honesty and making sure a level playing field is created for everyone, because we have like distance students and all these other students who don't have the luxury of working face to face with people, and I don't want people to take advantage of that here. And so you got 2.5 hours to take it, and then students who are here or we're taking this class as an asynchronous online class, it'll be open for a certain period of time, probably like that Tuesday to Thursday, and then you can take it anytime during then if you're taking it asynchronously. So when performing geostatistical analysis, we find patterns or clusters when analyzed at one scale do not yield the same patterns at a finer scale. What's that called? And I just talked about this, so this one might not have settled into the brain yet here, but no, this is with scale. So modifiable area unit problem, okay? MOP, meaning, all right, I've got zip codes versus, quadrants, fine scale quadrant. And I got 2 different sets of patterns clustering based on that. Reaching a conclusion that goes against what data dictates. Because at the end of the day, what are we doing? And you hear about this in football, basketball, this whole idea of analytics. What is the idea of analytics? Should you go for it on 4th and 2? Exactly, probability and data. We have all this data at our fingertips. Can the Dodgers have a bullpen game in Game 3 of the World Series? And apparently they can, and still beat the Yankees 4-1. So, apparently they can. So, but because of the use of analytics, hey, the third time someone goes through the batting order in baseball, you better take that person out no matter how well they're doing. So, the days of feel like and, look like and what do I think? Those things are over for the sake, because of data-driven decision-making, things that our eyes and ears and senses can't really sense because we just don't have the capabilities to process that much data. Okay. Reaching a conclusion that goes against what your data dictates is what? The exception policy. I know someone who, whenever someone says that to me, I just say, yep, you've just proven my point when you make a beeline for the case of so-and-so, so-and-so who's done this or done that or whatever, and, kind of ignore it for something. In running correlation and regression analysis, and I'll let you, we're not going to answer this one. The value we're trying to predict is called the what, while we're using one or more whats. We have things called independent variables, dependent variables. We got residuals right there, and make sure these terms are applied correctly. Number 4, when performing GIS analysis, we find that regions tend to have higher counts of regions and lower populations. The process of blank might better elucidate what's going on and highlight rates within these. What was that big fancy word that Jocelyn used in the back? What kind of data do I love? I love normalized data, exactly. That's what like football wins in a season are, they're normalized. Median household income is normalized. So get a good idea as to what entails normalized data. I think most of us in this class do. Age grading is normalizing the normalization. You know, why? Because there's going to be certain things like death rates, which are going to be skewed towards certain populations. So when we age grade something, we're basically making the average age of every county or enumeration unit to be the same, because we know in death rates, when you map death rates, just you're mapping where all the old people are. You know, that is, for lack of a better term. When performing geostatistical analysis for an entire region, we may get data from one part of a region using one set of methods. Oh, this is a different, oh, this is logical consistency, okay? All that means is I'm getting the Durham, I'm getting the data outside of outside of the city from sheriff's office versus inside of the city from the police department. They have two different ways of collecting data, systems, attributes. They're not going to be able to mix and match, you know, as nicely, because one might be used universal crime reporting standard versus the incident-based reporting system, which are like going to double your numbers. Explain the difference between a local and a global to measure spatial autocorrelation. This big fancy word, spatial autocorrelation, what's that mean? Hope you know what it means before you start to put in the answer. What does the autocorrelation mean? Spatial autocorrelation. The idea that things near each other are more related than things further away. It's just the personification, exemplification of Tobler's first law of geography. That's it. You know, and you know, Tobler did this back in the 70s, but now we got this GIS stuff that can do this really easy, really easy. The spatial autocorrelation is just how well do things near each other match up or align or measure than things that are further away. Because we should have highs next to highs, and they go to mediums next to mediums, next to lows next to lows, because we know in reality on a map, everything can't be high, right? They can't be high values, because what's the definition of high? Above the mean. That's it. And that's what our hotspot analysis does. And so even when we run our gas org and gets hotspots and cold spots, we still run into issues when we deal with extreme outliers, which skew those things. Okay. I'm creating a fishnet. Okay, I'm creating a fishnet for this entire study area. I'm going to run a spatial join between my quadrants in green and deer vehicle collisions in Guilford County. I might get errors because of what? What is the obvious thing that you see if I run a spatial join between these greens and these points? What's the big problem you see? Edges. What's wrong with the edges, Michael? You're right. What's wrong? It's uniform. What's so ununiform about them? You're on the right track.
The squares are not of equal sizes.
The edges are equal sizes, but what about the squares? Some are in, some are out. Some are on, some are off. So if I run a spatial join, I'm going to get a bunch of zeros here. I run a spatial join on this. You're only running the spatial join on part of the county. What can you do to circumvent that? That's a good answer, Michael. What can we do to circumvent that? Two things you can do. Smaller area. Hey, I need to run a select by location, so I'm going to get the quadrants that are entirely within, or hey, let me collect the deer vehicle collisions from like a 5-mile buffer outside. You pick. You'll get a slightly smaller sample size, but we're working with this sample size. We're working like 20 by 20. We're working with 400 here. I'm pretty happy with that.
So, for this case, right, depending on how big it is, can you use the like a hexagon instead of the
You can, but I'm not a hexagon guy yet. I want to be a hexagon guy, but I'm not. Because in the crime analysis toolbars, it'll actually go and create hexagons. And they're starting to get into the hexagons. I'd be interested to see how the hexagons compare. They shouldn't compare that much differently, but I'm just not there yet. I'm still old school with this stuff. But hexagons are being integrated in the crime analysis package. Because we have crime analysis that does clustering, and all it does is a nice little spatial join and does this without telling you you're doing a spatial join, because crime analysts probably know how to run the tools. They don't know how to do the spatial join and the data creation and all those other things. So we've got some data that go through and create this. I run quadrant analysis. If there are 1,000 vehicle collisions with an area of 500 square miles, compute the length of each quadrant. Sometime in quadrant analysis, didn't I give you a little formula, like square root of 2 times n over L? Yep, I'd look up that one and just plug them in there. Compute the quadrant, the area of each quadrant. If I know the length, how do you compute the area of a square? Length times the width, or the length times itself, because the length and the width are the same thing. Okay, so those of you, there's a formula sitting there. Go get the formula, plug in the values. Yep, oh, thank you, Durant. If I were to increase the size of the study area, but the number of vehicles, deer vehicle collisions remain the same, what would happen? And just for the heck of it, I'm going to go to this presentation to make sure I have the formula so I can write it down. What vehicle? What? I think this is it. Come on, where are we? Don't I have a Poisson distribution here somewhere? Come on. Am I hiding the formula here? What do I do? What do I blame here? There we are. 2 times A over N. The length. So the length equals 2 times the area, and I'll point this to these folks here. Oh, they can see it on the screen, okay? But length equals 2 times A over N. So if we go back to this, if you increase the number of deer vehicle collisions, is that L, A, or N? Deer vehicle collisions. N. You increase N in the denominator, what happens to the number? Does it go up or go down? Goes down. Okay, if A goes up, what happens to the number? Goes up. I asked you by a factor of what? Okay. So increase the size of the study area. Next, you can see I ran a spatial join. And so this is taken from a real calculation. If I'm really motivated, I might go and no, I'm not going to redo it. Use the same thing, please. I say if I'm motivated, I'm not going to be motivated. That's just not. Okay, so this is the real calculation. So sitting in the final exam, I already got the quadrant analysis sitting right here. Okay, so you can see I ran a spatial join with the observed number of grids for a study area, right? So this is the observe. I ran the spatial join on my deer vehicle collisions. I saw that there were 56 grids with 0. 105 with 1. 115 with 2, 91 with 3, 35 with 4, right? So we can graph that, right? And basically what I want to do is compare it to a Poisson distribution. Given funny backward symbol equals 2.014. What does that thing mean? How did I get that number? What does this thing mean? How could I get that? Excel, how do I get that? What do I get that funny number? What do you think 848 divided by 421 is? Yes, exactly. You did that in your head? Or you did, okay. Okay, so that's where I got that number. The average, I know we do these things like the average number of soccer goals per game. You can predict, how many games are gonna have 7 goals, 6 goals, 5 goals, and the average, it's probably like 2.5 goals or something like that. Based on that number, total number of goals divided by total number of games, and that's the average number of goals. But when we do have Poisson distributions, you can't have 2.7 goals in a game or whatever. It's got to either be 0, 1, or 2, or 3, or 4. And that's what the Poisson distribution really does with these count data. So we have this average based on 848 gear vehicle collisions and 421 grids. So that's the average. And so if I were to pop that number up, and we can play with this a little bit if you want, but oh, good. We're going to play with them now. We'll show an example here. But so now the expected proportion is going to be what? Equals what? POI Poisson. Poisson distribution. Okay, so what does the Poisson distribution ask for? The X. What's the X? This little number right here, right? What's the mean? That little, I think, what is that, lambda? 2.01425.178, comma, cumulative, yes, we'll type in true. There it is. And so now in a real Poisson distribution, there's a 13.3% chance versus a 13.3% chance. Wow, that's not bad. Okay, here, what I'll do here, instead of true, I'll put false. Did you notice what's happening here? What I saw here was a 24.94% chance versus a 26.87% chance. Now, how do I get the expected number of grids here? How do I get that expected number of grids? I multiply the chance times what? Total number of grids. I bet if you were to add all these up, what do you think this is going to add up to be? 421. I bet if you add all these up, what do you think they're going to add up to be? 421. They better be. So this column is just going to be equal to this column times 421. And I can just drag this down. And if I were to look at the sum here, it's about 421, right? Now, what's the problem? Can I have 56.1699 grids? No, I can just round it, right? Round, comma 0. There we go. So 56. There we go. And look what it adds up to be, 421. Do you think that's a coincidence that that's 421 and that number there happened to be 421? No, definitely not. Now, what's the whole goal of this? Because a lot of times I like making these grids, and even when I started teaching this class and saw these things, they were like, what are we really trying to do here? What do I want to do? This is inferential statistics, if this helps you any, but what do these inferential statistics really do?
It's trying to see how far away from the expected.
Exactly. How far are we from random, or how close are we to random? This is just a random distribution. That's all it is. Instead of being a nice little normal distribution, the normal distribution starts at the 0, right? You can't go to negatives. But all it is just a nice little normal distribution. And this is what we saw. So how close is this to this? 56, 113, 114, 70. It's pretty darn close, isn't it? Real close. Now we use that Kolmogorov smear-off test to test how well it is. But if I want to do just for the heck of it, watch what I do here. I can do this, I can do this, and I can do insert. Look at that. That's pretty darn close. That's nice. You know, and you got papers here, you know, ready to go with this stuff. I wrote a whole paper on bear collision, you know, bear sightings in New Jersey just based on this. You know, and if you wanted to, you could probably apply this to like crime or whatever, you know, because these are counts, you know. At the end of the day, remember, these things are going to be counts. So if we're looking at crime rates, we go Gaussian. Here we use Poisson distributions. Now, the other kind of funky thing right here is, you know, if this average were a little different, you know, instead of 2.1, you know, if this were like 2.5, then these numbers would be a little bit different, right? They'd be skewed a little more into the 2 to 3 direction, right? If it were 2.5, right? So this number is important, right? Now, if it were 2.5, then we'd probably have slightly different quadrant sizes based on this. So we'd have to go back to do it all based on the L equals 2 times A. But that's what it does here. You know, imagine we had something like, you know, something funky like here, like 6. Well, that's what 6 looks like. And this is what like 1 looks like, you know. So that's what a Poisson distribution looks like with like a 6, you know, versus a 1. Like a 1.04.3, and then so you can see these different, you know, these differences right here. What that Poisson distribution, what that Poisson is going to look like. I forget what that other one was, or something like 2.1 or whatever, right? Boom. All right, we feel good about that table there, because you can play with the table, bring it in, and guess what? Fill in some answers. I'm not going to be motivated enough to make a new table. I just, so A, B, C, D, all of these here, create a graph. What's the graph tell you? Okay, I'll let you figure that out. I have 2 different sets of points for a region, Rockham County, then Guilford County. These are most clustered. After extracting the data locations, I get P values. I ran an average nearest neighbor to determine the level of clustering. Tell me how the nearest neighbor is calculated. Don't cut and paste, you know, really nearest neighbor. When I find my nearest neighbor, what am I doing? I got 50 points right here. What does nearest neighbor do? I'm at point 1. I find my distance to the nearest point to me, wherever it is. Go to the next point, I find my distance to the nearest point. Go to point 5, 6, 7, 8, and I just average up that number. That's all I do. Now, what do I compare it to? Something along the lines of this calculation that has a average random distribution. If I had just threw out a bunch of random points in comparison to, you know, if the average distance was 1 mile versus 1 mile, it's probably going to be random. If it's 0.5 miles versus 1 mile, it's probably going to be clustered. If it's 2 miles versus 1 mile, it's probably dispersed, because dispersed has a level of intentionality attached to it, meaning they're all equally far away. And random, some are far away, some are close. And clustered, most of them are close to each other. And so we have that continuum on both sides of the Z, or the both sides of the P right there. So you can see I've got a Z and I got a P. You tell me what these things mean. So tell me what this means. Tell me. Don't tell me now. Tell me next in 2 weeks. Okay. If we were to run Ansel and Moran's I, inverse distance for average family size, you would be one county classified as low high. What's low high mean? Why aren't there no other low highs out there? Running cluster analysis. What's the definition of a neighborhood? Ooh, we talked about all the different types of definitions. I showed you two cluster maps, where same exact data, we use different definitions of neighborhoods and they appeared exactly different. '22. World Health Organization. Look at this. And this is this little chart right here. Height versus weight. So according to the World Health Organization, if you know someone's height, you can predict their weight. Which one's the dependent variable? Which one's the independent variable? Weight is dependent on height. So if I know your height, we can predict your weight. Can we plug this little formula in right here? What is your predicted weight? Equals what? 3.9668783 times what? What is height? The B cell minus 124.691. There we are. So according to the World Health Organization, if you are 56 inches tall, you should be 97.448 pounds. Pretty neat. This is what we do here. This is really truly regression. Now, according to this equation, someone who weighs 160.91 pounds should be how tall? Okay, let me just go to that there. They should be 72. I might change these. So, don't look for the exact answer. You know what I mean? I might say, hey, 97.448. And people call up and yell at me and say, hey, I couldn't copy your exact answer that you gave last week. And well, because I changed it. You actually have to think. Okay, so next, residual equals actual minus predicted. So equals, what's the actual? All right, the C comes to this. Okay, and I'm probably going to change that. I might be motivated to change this table around a little bit. But now, what do the positive means? What do the negatives mean? What's the positive? What's the negative? Okay. What's the positive? This person who's 7, are they higher than what they should be or lower than what they should be? They're higher. So what do you think these negatives mean? Lower. And in theory, if we were to add all these residuals up,
Here's what I found.
I don't need you, Siri. What did I just say to you? Stop. Thank you, though. In theory, these residuals should add up to 0. They don't because I don't know what I did. Now, what can we do here? We can graph the height and the weight. Uh-oh, nope. That one. There we go. So we got there. We got a nice little scatter plot right there. Watch what we can do. Right mouse click. Add a trend line. This equation kind of ring a bell to what we're looking at right here? See this equation 4.4.34? I was doing that World Health Organization, so I'm just going to blame them. So, but you can kind of see the same. We got a y-intercept. We got a slope. So you can see this one here versus this one here. All right, so hopefully, not hopefully, we're all going to be able to answer what person has the highest negative residual. Furthest from, and I changed this question last year because I had people arguing with me that numbers like -13 are larger than numbers like 8. Like, yes, you just shook your head. They really argued with me. They're like, -13 is bigger than 8. No, it's not. So I had to explain explicitly, like, which one has the highest negative residual? You know, because I put like, which one has the lowest value? And they're like, well, -1 is lower than -13. No, it's not. -1 is a bigger actual number. So I want to make sure this reads semantically correct. And I want to make sure when we're looking at this, this is the one and that's got the lowest number, lowest negative number, furthest from 0. And that's what kind of why I explained it from there. Because, you know, all right. What does it describe? Which of the following best describes spatially? There's only one question on spatially weighted regression. Okay, that's it. We're done. That's what we talked about last week. Okay. I run single factor regression on using OLS. See if there's a relationship between diabetes death rates. What do you see? I gotta figure it out too, to be honest with you. So, okay, yes. Let's let you all figure that out. But what are the things that we care about? Probabilities. Probabilities should be what? Lower the quote unquote better or supporting our thesis. Okay. So here we're looking at our robust PR right here. This is a t-value, which kind of equates with a z-score. We don't care about the intercept right here, but we're looking at these values over here. And I kind of threw all this stuff. And where's your adjusted R squared? What does that adjusted R squared tell you? Is there a big relationship between the two? No. No. Just for the heck of it, watch what happens if I were to put an R squared right here. .97. So this is the 0.97. This is where I kind of encourage you to work smarter. This is a 0.000370. So what's that going to tell you about that set of points versus the other set of points? Totally opposite end of the spectrum. Is there a correlation or relationship with these? Yes. This says that 97% of weight can be explained by height. What accounts for the other 3%? Other thing, diet, all the, genetic predisposition, your lip, your habits, all these other things here. So 97% of it in this model here can be explained by height alone. Pretty interesting. Only 3% of it can't be. Okay. So going back to this, what percentage of diabetes can be explained by, what percentage of COVID can be explained by diabetes? 0.0000370. The other 99.993 is explained by other stuff. Does that make it a strong relationship? I run singular regression analysis again. By male explained by COVID-19 rates. Will I explain this here? All right, now I ran some things in Excel, ANOVAs, metropolitan, micropolitan at the percentage of unaffiliated. So I have metro, I got micro, and I've got rural. So in metropolitan areas, we got 32% unaffiliated, micropolitans 31, rural 30. And I have an assumption that, hey, unaffiliated, what's unaffiliated voters mean? I'm one, proudly. I am not registered with the party. The Green, Democrat, Republican, I just go in and just pick whoever I like. No, I'm just kidding. They really don't care. But so we can have it some. So when we do multivariate ANOVA, more than two, we just do the two-tailed t-test, but we bring in an extra variable. And so the assumptions with these are that unaffiliated, and we kind of go back to what's our null hypothesis going to be? Unaffiliated voters are evenly or equally distributed across metropolitan, micropolitan, and rural communities. So I could say, hey, there's no difference between rural, metro, and micro unaffiliated voters. They all have the same what? Percentage. They're all about 30%. Now, what does this ANOVA tell you? What's that p-value tell you? No, because in theory, because once again, this is an inferential statistic, right? What does inferential mean? Compare to random. So in theory, they should all be 31, 31, 31. Now, if one were 31, one were 30 and a half, another were 30 and a half, then probably this p-value would be much higher. But we got a value almost difference of 3 percentage points across 381, 191, and 191 sample sizes. So your margins of error are going to be a lot smaller than the 15 that we were looking at before class. So that's why these margin of errors are going to be a lot smaller here. So what can we say? Can someone put in the words, what are we saying right here? Tell me in words. Are unaffiliated voters equally, or is it the same for metropolitan, micropolitan, and rural? No, they're different. Can I say which one's higher? It looks like metro is probably a little bit higher. Do I know why? I'm definitely not answering that question. No. Go over to poli-sci. No. Yeah, I don't know. I don't know what the answer is. I'll just look at my answer key and I'll let you go. Or let you answer me so I can answer. Now, some of the things about this: spatial interpolation, PM values, control points, number 1 through 5 in black squares. I've got control point 1, 2, 3, 4, 5, meaning we know what the values are right there. Why? What does interpolation mean? Filling in the missing values based on known values. That's it. Temperature, PM, whatever. So I know what the value is here. Now, what are the different methods we use? Priming, splitting, and and I'm a big IDW fan, but if you get into climate, you get into PM, there might be already research that says, hey, splining is the way to go, or maybe you're gonna be the one out there who says splining is the way to go with some of these. There's lots of opportunities out there for this. What do we know? Basically, things that are closer have more of an impact. So on this surface, I got Durham versus level number 3. I bet you if I run Craigie versus Splining versus IDW versus nearest neighbor, I bet you all the values around Durham are going to be really close to each other because they're really close to number 3. And so when we run PM values, we might run into some Craigie and Splining that get negative, which we know is impossible, but we don't, well, I don't have enough time to go through the environments and say, hey, get rid of all the zeros or whatever. We just let it run. What else we got here? Oh, wow, 6:48. I'm sorry. Oh, I'll hurry up. Let me get this done. Let me just idea behind different types of interpolation. Yeah, got different interpolation routines. When you run 33, when we run spatial interpolation using default settings, the extent of your interpolated surfaces will be the extent of your control points. What environmental settings do we set? So I would go through some of the interpolation routines that I have there to change those because you had to go through and change some of these. Next, I brought a two-tailed t-test that say rural COVID-19 rates will be different than urban COVID-19 rates from the same time. You can see the results. What's it tell you? What's that really low p-value tell you? They're different. They're real different. Right? What are the difference? We have an average of 318 versus 443. What are the chances that we have a difference of 250 COVID cases per 1,000 people? What are the chances that we have this difference based on random chance alone? 0.0000526106. Is that high or low? That's really, really, really low. So what does that tell you? Something else is impacting COVID-19 rates. I don't know what it is. You go figure out what the difference between the urban and the rural are, because my definition of urban and rural might be different than yours, but we're not going to get into those rabbit holes. Oh, and that's it. That's the end. Okay. So we'll see you all in 2 weeks. Basically, I'll post any outstanding stuff, but everything's done except the position paper. Me, I have high expectations for the position paper because I want this to lead to a journal article, paper submission, something like that. For me, for PhD students, even faculty, I get, and I'm on the tenure reviews, and the biggest thing that people run into that have been here for like 7 years is that you don't have any papers. Why not? You just wrote a dissertation, pop out a paper or two. You're taking this class right here, pop out a paper into the North Carolina geographer. I'm on the review board. You'll get something there. You might get some comments back, change this, change that. But we're always begging for papers, and most importantly, begging for student papers. And this is the perfect form to do that. I'm not pushing the North Carolina geographer or anything like that. Submit it to something even better. So, and I get frustrated when, people curse at me on campus because I didn't give them tenure or whatever. And it's like, dude, you didn't do your paper. I'm just doing what, everyone said, you know what I mean? And that's a real hot button topic, not only here, especially like PhD students, you get your 3 papers done in a year. Guess what? You're done. You can get out of here and get done and on to bigger and better things and go solving world problems instead of writing papers for me. Okay, and we got undergraduates here submitting papers. Cameron's submitting papers. He's going to be talking a little bit tomorrow about some of the things he's done. So take advantage of these paper opportunities, especially when we have a forum here where you got to go solve a problem. You got to go answer a question that you know, I'm gonna really kind of look at and say, yeah, I'm no on this one. I'm gonna, you know, we're gonna start here at an 80 and work our way down, as opposed to this is a really interesting question, but you need to turn this into something yesterday. You know, and I'm always looking for ideas because we got people who come in with great ideas, and I'm just here to steer you in the right direction because you all have so much more talent, opportunities, and lack of limitation. No one's limiting to you with, you know, the data that are out there than I had for me, you know, 20 years ago. So talk over, go out and do great things, and I'll see you in 2 weeks. I'm done. 34.